Hello, this is a video to help out with the idea of moment of inertia, what it is, and how to think about it, and also a couple applications of it. All right, so before we jump too far in here, let's take a look at, from the reading, let's take a look over here at figure 9.16, where they've got this point mass, some distance from the axis it's spinning about, and then they've got one over here with M1 and M2 on either side. You should spend some time with example problem 8, but the big thing that comes out of example problem 8 is that I is proportional to mr squared. And they're using L in there, which is perfectly fine, okay? But the big idea you need to get out of that is that I has to do with the mass of the object and the distance it is from the point it's rotating about squared, okay? And that's the thing you're actually responsible for. You're not responsible for knowing all these equations that you guys see here in table 9.1. Okay, I would know that for a hollow, thin-walled hollow cylinder or hoop, or for a point mass, that you can just take that mass times r squared and get your moment of inertia. But even that one, really, you should be okay not remembering that that's that special case. But certainly these other ones with the 1/2 and the 1/12 and the 2/5 and all that, you are not responsible for. So if you're doing a problem, you need to look those up. That's fine. On the actual free response test, those should be given to you. Okay. All right, so now let's take a look at some applications. Okay, so now we know that I is proportional to mr squared. Oh, and I'm going to go ahead and redraw that, or that you show that idea again here. So let's say we're rotating about the spot with the dotted line. Okay, and I'll have some mass here, m, and I'll just call this r1. And then drawing this somewhat to scale, here I have a different r, but the same mass. Okay, even though this object has the same mass, if we're spinning about this axis here, the dotted line, this one on the right has a bigger moment of inertia. Or you might want to think of it as rotational mass, because this moment of inertia, this I, is our stand-in for mass when we rewrite the equations for things in terms of rotating bodies. Okay. All right, so this one has more, this one has less. Another way of thinking about it, if you don't want to think about a point mass, is that it has to do with the distribution of mass. So if you've got more mass near the outside, okay, versus the inside, you're going to have a bigger value, again, of I. Okay, so now let's go ahead and apply this a little bit to our idea that we can sum torques, and that's equal to I alpha. So this is similar to our summation of forces equals MA. Okay, where we can add up the torques, okay, and that'll be equal to our stand-in for mass times our stand-in for acceleration. This is our moment of inertia, or a rotational inertia, or if you want to call it rotational mass, that's fine too, but typically people call it moment of inertia, times our angular acceleration, similar to what we had over here. So if you have a bigger moment of inertia, it's going to take a bigger summation of torques to get the same alpha. If you have a smaller moment of inertia, it will take less torque to get that same alpha, or however you want to think about it, but similar to F equals ma, right? If you have a really big mass, it's going to take a lot of force to get some acceleration that you're looking for. If you decrease the mass, it's going to take less force to get the same acceleration. So you can compare it to those ideas of F equals ma, and that all still works the same. Okay, so now what we're going to do is let's talk about it in terms of with angular momentum. So if you remember, momentum, P, equals mass times velocity. For angular momentum, we call that L, and L equals I, our stand-in for mass, right? And then what's our stand-in for V? That's our omega, our angular velocity, or angular frequency, but typically I'll call it angular velocity. So I omega versus mv. All right, and just like with momentum, sometimes we can talk about when momentum is conserved. Okay, so when is this delta P going to be 0? When the time outside forces have to act as 0, or when the external forces are 0, delta P will be 0, and that's when momentum is conserved. Similarly, we have an equation, torque, our stand-in for force, right? That's a tau. Delta T, still time, okay, equals our change in L. So this is like our fat app equation, and this is tattle, because again, these look kind of like A's, right? Okay. So our torque, our external torques, got to be careful there, external torques, summation of those external torques, times the time over which they act, they can cause a change in angular momentum. So the question is, when will angular momentum be conserved? So if our external torques equal 0, or if that delta t is 0, right, or really, really small, similar to our fat app stuff, that means our delta L will be equal to 0, or L is conserved. All right, so our angular momentum will stay the same when we don't have any of those external torques, or they don't have much time to change the angular momentum of our system. So let's go ahead and put this into an example here. Oh, and I'll be using, I'm going to rewrite this down here a little bit bigger, L equals I omega, and I am going to try to make it so that our angular momentum, at some point in the example I'm going to show, that our angular momentum should stay the same. And let's see what happens with our I for this process. All right, so let me switch over here to, nope, not that one. There we go. All right, so I'm in a swivel chair right now. It's not the best scientific apparatus because there's plenty of friction as I spin, which would be an external torque, but let's pretend that's not there, okay? And let's say I start with my hands and legs out like this, okay? So my mass, I've got a lot of mass. Think of my fists and my feet as point masses, okay, far away from me. I'm going to bring those point masses in. So, and I'm going to do this while I'm already spinning. So to get myself spinning, yes, there's going to be an external torque. There's going to be a torque as a result of my interaction with the ground because I'm going to push off. But then once I'm spinning, I'm just going to sit here and we're going to neglect friction with the tire, or sorry, with the chair. So in this plane like this, I'm not going to worry about any external forces or torques or anything like that, okay? So I'm not going to have any external torques. That's my approximation. And if I'm already spinning and I pull my hands and arms in, should I go faster or should I go slower? So think about that L equals I omega. We're saying L stays the same. Think about what happens to I, and then as a result, what has to happen to omega. So here we go. I'm gonna go ahead and start myself spinning, and now I'm going to pull them in. And I started going just a little bit faster. Okay, now here's why. Let's go ahead and go back to the paper. All right. So when I pulled my arms and legs in, it's as if I went from this picture to this picture. Okay, so I made my I go down in that case. Okay, why? Because I was making my R go down. I was moving some of my mass in closer. So when I'm figuring out what's happening to my I, it decreases. Okay, so what does that mean? If I is going down, right, and L has to stay the same, omega has to go up. My angular velocity has to increase. And we kind of saw that, okay? I went ever so slightly faster. You may or may not have been able to notice it on the video, but I felt it. I got going a little bit faster, okay? Especially when you consider the fact that there is some actual external torque that would tend to make me go slower. I at least maintained, if not went a little faster as I kept going around, okay? All right, so let's do another one. And we'll apply this L equals I omega idea again. All right, so this time I'm going to start with my arms and legs in close as I'm spinning around, and then I'm going to throw my arms and legs out. All right, get some space here. Watch the cord. All right, so I'm going to go ahead and have an external torque with the ground to get myself started. Okay, and now no external torques. I throw my arms and legs out, and I didn't notice anything. So let me try that again one more time. I'll get myself spinning a little bit faster to begin with. Throw my arms and legs out. I may have slowed down a little bit. It's a little bit tougher to see or tougher to feel this time. Not sure why. Let me try again. Maybe I don't have probably because I don't have my legs in close enough. Here we go. Let's try again. And then, there we go. That time I noticed it. I slowed down a little bit. Okay? All right. Now, why? Oops. All right. Oops. Somewhere in here. There we go. Okay, so why did that happen? So this time I had my arms and legs in close, so I looked like that. Threw them out, okay? So my R would actually go up. This number would be going up. This would be staying the same, so I would go up. So my I would increase. My omega would have to go down. So my I goes up. My omega goes down. So that was a quick little review and application with our moment of inertia ideas. Think about it as distribution of mass. So if you've got your arms in close, okay, you have brought your mass in closer, you've made your I go down. It's the ice skater trick, and you're going to spin faster if you're neglecting external torques, right? Because your angular momentum would stay the same. If you're spinning on ice skates and you throw your arms out, you're going to slow down. Okay, so you can picture an ice skater when they bring their arms in close and they're already spinning, that they spin up really, really fast. They throw their arms out, they'll start to slow down if they want to skate off and do something else. That's because they're changing their distribution of mass. They're changing their moment of inertia. If you guys have questions, just shoot me an email, or you can show up for office hours. And that's it for this review of moment of inertia. Have a good one, guys.